On the Nintendo 64 in 1996, you got exactly 4 megabytes of memory, and that was it. This fits only about 1350 average Mario 64 resolution level textures. Of course, not only textures are in memory, but also code, the game engine, music, output buffers, and temporary actor states. Games had to store all this data within a memory about the same size as one single picture of a modern smartphone camera. In some levels, such as Mario 64's opening map, space was so tight that just 2 extra sludgy 32 by 64 textures would have made the game run out of memory. Because of that, N64 developers often pulled out tons of tricks and optimizations, and sometimes even had to make sacrifices to fit data into these 4 megabytes. So what tricks were used in Mario 64, and which sacrifices were made? Mario 64 uses all 4 megabytes of memory exactly, despite the cartridge only holding 8 megabytes of data. But what if I told you a huge chunk, about 93 textures worth of data, of this was wasted due to 2 separate typos, each wasting about half of that extra space? And how much memory did Mario 64 really need? People like to say that modern games are extremely wasteful resource-wise.
I'm talking, of course, about the rapidly spreading virus in gaming right now, known as bad optimization.
But were old games really that different? Could we theoretically maybe even fit Mario 64 onto the PlayStation 1's much smaller 2 megabytes of memory? Have we simply been using hardware in wasteful ways to cut down on development cost and push that cost onto more expensive hardware all along? We will find out today, and I will even show you guys how Nintendo improved on this a lot in the later released Ocarina of Time. Please be aware that as long as your game fits into memory, there is no point in optimizing the memory further. So unless they had to make sacrifices, reducing memory usage is pointless. Nonetheless, we can speculate that if they had not run out of memory, they might have added more details and textures to the level, and maybe they could have used a technique we call memory banking, which gives you a roughly 5% performance boost. So sit back and let me take you on this little adventure into the inner workings of Super Mario 64. Let's first take a look at Mario 64's RAM map. This is how all the data is laid out in memory at runtime. We start with 1 kilobyte of exception vectors and configuration stuff as the Nintendo 64 manual recommends. Then we follow with about 1/3 of a megabyte for the Z buffer. Then we have around 1.5 of megabytes of memory pool for actor and level data. Then we have around 0.5 megabyte of music data, followed by 1 megabyte of code, followed by 1/4 megabyte of variables and actor states, followed by 1/8 of a megabyte of engine code, and then we end with 0.5 megabyte of frame output buffers. As you can see, all 4 megabytes are used exactly. Let's go over all the parts to see where we could save memory. We will start at the very end of memory, because trust me, this will make our life a little bit easier. The last address in memory is hex 80400000. The 4 stands for the 4th megabyte. In the RAM map, you can see that the frame buffer goes from hex 8038F800 to the end of memory, which is around 0.44 megabytes. Since Mario 64 outputs a 320 by 240 image and has 2 bytes per pixel and is triple buffered, which we need it to be, there's really not much we can do about this. Except, do you see these black bars at the top and bottom of the screen? These are always drawn. They likely existed to combat old TVs and their overscan issues. A silly thing that I myself have forgotten in my most recent demo, leading to slightly ugly heads-up displays. Since all 3 frame buffers are continuous in memory, technically we could overlap them like this and save the memory for 2 black 8 by 32 strips in the middle of the frame buffer. This saves 16 lines of 320 pixels or hex 2800 bytes, just about enough to store 3 average Mario 64 textures. Maybe there's even some way to simply not render these black bars and just output a 224 by 320 image, which would save 3 times as much, but I wouldn't know how. After the frame buffer, we have hex 910 bytes of empty space. Yeah, I didn't even mention this yet, but Mario 64's programmer have manually told the compiler where to put each piece of memory instead of letting the compiler pick the memory locations, leading to a lot of gaps between data that are just empty space. This might sound like a lot of waste for now, but that's honestly nothing compared to what we will see later. You have to think of a programmer as the architect and the compiler to be a builder. What do I mean by that? Well, maybe this video sponsor boot.dev can explain that a bit. They have courses on memory management, and hey, maybe you'll understand more of this video if you understand their course. Many people ask me how to get into programming, and this seems like a very simple way to do so. All their courses to me seem well structured, and even if you do get stuck, they have solutions available for every challenge on their site. They have courses for many programming languages, so whatever your goal in programming, I'm sure they will be helpful. I always tell people that the best way to learn programming is by doing programming, so this website is actually great. You can read and watch all their content for free in guest mode, or even try their free demos. And if you like what you see, you can start a subscription with them, on which you can get 25% off with code Kaze. Plus, they have a 30-day no question asked refund policy, so you really cannot go wrong with their program. Anyway, back to the programmer being the architect and the compiler being the builder. The architect here basically told the builder, put section 4 at location X and section 5 at location Y, which of course will lead to some unused space between these sections. A more reasonable approach is to tell the compiler to just put it in the next free location. This also saves programmers a lot of time, because you won't have to constantly adjust your memory addresses while you develop your game. Moving on to the next section, we have a much more significant memory saving, the engine segment. This section interprets level and actor scripts and compiles armatures and collision data from a compressed format stored in the ROM to a faster to process, uncompressed format in memory. The first obvious improvement here is to compile the code for size. The N64's memory is so slow actually that code compiled for size typically runs faster than code compiled for speed. I have never seen it not be that way. Of course, Mario 64's code was compiled for neither. The release version of Mario 64 in the US and Japan were actually compiled for debugging. Look at the C code to add two vectors. Here's a comparison of what Mario 64's code looks like versus what the code compiled for size looks like. Even if you may not be able to understand the assembly here, you can see a lot of repetition is going on and a couple useless comments are left over in the ROM. I picked a very simple free line function here. The difference is much larger on more complex functions. Compiling for size roughly halves the size of the code segment. But not just that. As I've said, most of this code is just used for compiling collision and armatures. It is not actually needed outside of loading zones. In other words, about half of this engine code is just loitering in memory doing nothing most of the time. A perfect candidate for the chopping block. There's also a lot of code here for unutilized comments or code that is duplicated for no good reason. Some examples include a behavior comment to set a 32-bit value or an armature comment to copy an entire scene view. Hey, maybe this is leftover split screen multiplayer mode. That's like the best explanation for this. Anyway, removing all this would likely be an additional 50% reduction in RAM for this section for a total of 75% reduced. To be honest, I'm kind of spitballing with the 50% reduction here, but we don't need to be 100% accurate. This video is more or less about the principles of programming. We honestly don't need to be too exact to see whether we can fit this game into the PlayStation 1's memory or not. Another big memory save in the engine code are the math functions. The sine and cosine functions use one large table with 1 1/4 circle rotations. They share data, and the cosine function simply indexed a quarter rotation after the sine function. The normal way of doing this uses less RAM usually. You would use circle symmetries to half, quarter, or eighth the table size. Of course, we could even use a polynomial to save the most RAM, but since we don't want to sacrifice anything or change functionality to get more RAM here, let's go with the quarter interwoven sine table. Something I've talked about in this video here, to get a table that is hex 3000 bytes smaller while also slightly improving performance. This is roughly equal to 4 textures of memory. Moving on from the engine segment, we have a baffling hex 113A0 bytes, or about 23 textures worth of empty space. This is the biggest empty area in the game, but interestingly, it's nowhere near the biggest waste of space in the game. But why does it exist? Maybe they just had a typing error in the calculator and accidentally added a leading 1 to the total empty area size? Wouldn't be surprising, because later parts definitely had typing errors. Or maybe they picked a big offset because below the engine section is all the main code and its variables, and they likely wanted to be able to add a lot of code before running out of memory in that section. Which actually leads us to our next topic, the main game code and variables. Almost the entire variable storage area is taken up by temporary actor state storage. Each actor in the map gets a little mansion-sized hex 260 bytes of data, regardless of how simple the object is. Even something as simple as a stationary piece of level geometry like this, or an invisible, intangible object that does nothing uses the entire hex 260 bytes. The data is arranged like this. First, we have some important render parameters and a bit of metadata to link and unlink our actors from the active actor list. Then we have some often used actor flags, and then we have hex 140 bytes of data that is a mishmash of very important stuff, such as an actor's position and rotation, and some more rarely used actor-specific storage values. Ocarina of Time had a similar but much smarter system, where each actor had a small header that had necessary data and then stored additional data in the lower part of the memory. This is more akin to how C++ classes and subclasses work and would have saved a lot of memory here. We could simply not allocate the extra data required to store parameters that will not be used. Anyway, after all this extra data, in Mario 64 we have a collision pointer, hitbox stuff, some more metadata, and for some reason a whole 4x4 render matrix that can be stored and is sometimes used, but really never should be used because it just makes the game render slower. Just from looking at how much of this data an average actor in a level like Bob on Battlefield actually uses, I would say this wastes about hex 140 bytes for the average actor, or about hex 14500 bytes, 27 textures in total. This would be just over half the size for all these actor states. The object pool also always has space for exactly 240 actors allocated, even though every single level in the game uses less than that. I believe the most actors you can have without glitches or exploits is somewhere around 180, but I couldn't find any exact number due to how many factors go into this. Reducing the pool to that would further reduce memory usage by hex 4380 bytes. Although it being so oversized is what allows people like Pun and Coke to spawn dozens of clone Goombas to build a ladder into the sky here in Bob on Battlefield, so this memory save makes glitch playthroughs less viable, which is why I'm not going to factor this into our final memory waste estimate, because it does affect functionality. Before we move on to the code section, we need to talk about overlays. Overlay is a feature that is used in Ocarina of Time for every actor. Not only do they decide how many variables to dedicate to every actor, they also load in all the actor's code and variables. Mario 64 has no such thing. All actor code and all actor variables are loaded into memory at all times. While you are sitting in castle grounds here with 7 kilobytes of memory left in RAM, Dory the dinosaur's code is sitting idle in memory, eating kilobytes and doing nothing. The same goes for all actor related variables and even pre-made data like Toxbox paths. As you would expect, only loading in the relevant data instead of the whole codebase at once is a huge reduction in memory usage. Since only ever at most around 20% of the actual codebase is used, this will be roughly an 80% reduction in size across this entire area. The main area minus actor states is pretty much exactly 1 megabyte in total, so with this change we'd be saving hex CB000 bytes, or about 270 textures worth of data. Wow. If we wanted to fit Mario 64 onto a PlayStation memory, this would be by far the most important memory save. Although it does come at a very minor cost of having to load a bit more data whenever you enter a level, I would guess somewhere between 1 and 10 milliseconds of time. This code also has a lot of leftover debug code and is again compiled in debug mode. Getting rid of both of these would further reduce code size about 50%, leading to another hex 19500 byte game, which is about a tenth of a megabyte. But that really is it for this section this time. Next up is music data. Few Nintendo 64 games stored fully mixed music due to storage space constraints. Instead, they stored notes and instruments and then at runtime mixed those together into a background song. This requires some RAM to load in all the sequence data and waveforms used for the music. Instrument data is huge, and there's no way the game can load all instrument memory at the same time. Instead, to load instruments into memory, they used something the decompilers called the sample DMA buffers. The game can only play 60 notes at a time, each with a sample at a time, and there are exactly 4 sample buffers per note. When a note plays, its data is dynamically loaded into a sample buffer to seamlessly allow for playback. I suspect that they added 4 times as many buffers as notes to minimize the amount of ROM loading they have to do, but in practice I found this is not working at all actually, because sample buffers don't seem to be reused correctly. I assume this is because more than one programmer worked on the system and they just kinda broke each other's code. Kind of easy to break the system when the code looks like this. Logging the amount of new sample loads happening, it's obvious that the game doesn't ever actually reuse a buffer between notes, meaning 2 to 3 out of every 4 buffers are practically useless. That's what happens when you invite too many cooks into your kitchen. These extra buffers wasted about hex CA80 bytes of memory, which is around 17 textures worth of memory. Mario 64's audio system is a bit crazy, which is why I kind of just ripped out Mario 64's entire audio engine in my own mod and replaced it with my own, which now runs about 3 times as fast and uses significantly less memory. But that is not all for this region. This region is actually incredibly inefficient in its memory usage, and to prove it, I've written a code that at runtime investigates this whole memory area and keeps track of which parts are permanently left at 0. Then I wrote a code to sum up all the sizes of all permanently 0 areas and got a sum of hex 176C0 after playing around for a while, or about 31 textures worth. This is about 18% of the total music area size. Also note that this area is not just the sample buffers that I predicted were useless, as even the useless sample buffers are being filled with data sometimes. This is just data all over the area that never gets used. In the screenshot here, you can see all the memory regions in the music area larger than 256 bytes that the game never sets to anything that isn't all zeros. This means the total waste is likely somewhere between hex 176C0 that's permanently empty and that number plus the hex CA80 the game wastes on sample buffers. I'm not going to do the exact math again, but from the numbers in the screenshot, it looks to be around half of it is in the sample buffers, giving us a total of hex 1DC00 or about 40 textures worth of wasted data. Moving on to the next location, the memory pool. The memory pool is complex and holds all the geometry, texture and collision data for all actors that are loaded in the level, as well as all the other data we have allocated at runtime, such as compiled armatures and compiled collision data. This is another place where they did a bit of optimization. Only the currently played and levels data is loaded into memory, which does include all the sub areas. So for example, while you are outside the pyramid here, the inside of the pyramid and the boss fight area are already loaded in, although they are invisible and not in a playable state. Memory in this pool was actually super tight. Using Mario 64's built-in profiling tool in Castle Grounds, we can see that only hex 1A E0 bytes of data were left over in this pool, which is not even enough to store 3 average Mario 64 sized textures. That's kind of insane to see. I didn't think the developers were actually this close to hitting the RAM limit before I started scripting this video. This is due to a multitude of factors. Firstly, a lot of data is loaded, read once, and then never used again. Remember the code I talked about earlier that compiles collision and armatures? Well, the uncompiled collision and armatures stay in memory and never get read again after the first frame of a level's lifetime. Some of it even gets loaded during Mario 64's startup, such as Mario's armatures and armature for general purpose objects like trees or 1-ups, and then is dead memory for the entire game's runtime. Just armature data like that alone is already hex 2E30 bytes of Mario armature plus hex 1060 of general purpose object armature data of memory. And even when we do load the data we need, we load way too much. Mario 64 works in memory banks. If you wanted to load the Skeeter, you also need to load in the seaweed, the water mine, the water ring, a cyan fish, the treasure chests and the bub, due to how Mario 64's memory banks work. Ocarina of Time again had solved this issue by loading object data per room, one by one. And you've probably never even noticed any loading hitches going between rooms in Ocarina of Time, because this system is extremely efficient. But it's not just that. The data populating the memory pool is also wasteful. Often, textures were given full color channels despite being purely grayscale, wasting about half of a texture's memory. There are a couple more memory structures that are inefficient and used globally, but going into all these would be way too much to get into. Rest assured though that we could save a good bit of data. Combining it all, looking at the memory layout for Bob on Battlefield in the image here, I'm going to guess that we can reduce the buffer by about 33% or hex 75B00 bytes. This is roughly equivalent to 143 textures. And next up on our memory web, we have empty space. This empty space looks to be a typing error in the manually assigned RAM numbers. After all, the Z buffer can't possibly grow beyond the size it already was. This is tragic because this leads to hex 36800 or around 73 textures worth of literal empty space, and removing it is as simple as just don't put it here. Quick and simple. Moving on, we can't save much on the depth buffer, but remember the 8 pixel rim? Since the game never renders on the bottom 8 pixels, there is no need for this to be part of the Z buffer. Since the game never needs to write depth to those 8 pixels that are always black, we can just use it as data. And this is a very minor hex 1400 bytes of RAM, or about 1.7 textures of data we could gain. This one is admittedly a bit of a spooky hack for very little data that I'm not sure I would recommend doing. Adding all our saves together, we get hex 1E 5620 of memory saving, just under 2 megabytes. Well damn, we didn't quite hit our target of fitting the game into 2 megabytes. But wait, there is a secret 9th bit to every byte on the Nintendo 64, and I talk about it in this video here. We could actually use this 9th bit to store some extra info using dark magic, but to be honest, the strategy is expensive computing wise, and while it would get us below 2 megabytes on RAM usage, it would cost a lot of CPU cycles, so there would be harsh downsides to this. I suppose we could also either start optimizing the actual code or compromise on the object pool limit that I've mentioned earlier. After all, you can only get beyond 180-ish actors using glitches, so reducing the limit by 60 would not be a real issue. Anyway, we don't actually have to go below 2 megabytes to get this running on a PlayStation 1. Because while it is true that the PlayStation 1 only has 2 megabytes of RAM, it also has an entirely separate VRAM for the frame buffers, so we don't actually need to factor those into our memory equations. This puts us easily within our memory budget. PS1 games also used audio stored on the CD instead of mixing the audio and memory at runtime, so I suspect almost the entire music section here can be removed, and maybe we can even end up making this game fit into just a single megabyte of RAM. Maybe someone can use this video here as a blueprint on some of the refactors to get this game running on PS1. Anyway, I want to give a closing statement, so you guys don't get the wrong impression. While I did mention a lot of places that have missed memory optimizations, remember they likely had little use in optimizing the RAM any further. They probably managed to get the levels to look the way they want them to look. Of course, it is unfortunate that they couldn't use the RAM banking optimizations that lower RAM usage would have allowed for to get that extra 5% performance boost, but there are much lower hanging fruits optimization wise for bigger optimizations than that. And to be true with you guys, half of the stuff listed here, I don't do either in my game. My game of course has much larger maps thanks to my engine that can handle all that, which does require a lot more RAM, and maybe it would be possible to make my game work without the expansion pack by sacrificing that 5% of performance, but to be honest, I've resigned to simply using the expansion pack to cut down on development time. I would not be surprised if Nintendo went a similar route and simply did not optimize any of this to cut down on dev time, which is totally reasonable and understandable. After all, if there's no cost to using all 4 megabytes, why not use all 4? Thanks for watching this video, and a big shout out to all my Patreons for supporting my channel. I have been working on my own game called Return to Yoshi's Island 64 for quite a while now. We are slowly reaching the final stretch, and I am now working on the overworld to connect all the 15 courses and all the side levels and all the cap levels and all the boss levels I've made together. I'm working on this on my second channel, and I hope that soon I can get this finished. There's still a lot of polishing to do, but we're slowly reaching it. I also have a completely new merch store if you're interested. You can get your own Rambus shirt. That's it. Bye bye.